Space exploration. It's often depicted as a thrilling journey, but the reality for astronauts involves complex health impacts due to microgravity, radiation, and isolation. From a neurological perspective, spaceflight significantly affects the brain, especially the hippocampus, a region critical for learning and memory. Research using non-human animals and spaceflight analogs suggests that the hippocampus may be especially vulnerable to the stresses of space travel. We tested the hypothesis that spaceflight could negatively impact the hippocampus in astronauts who spent 6 months aboard the International Space Station. We collected data from 17 astronauts before and after their 6-month mission. To capture changes in the brain, we used susceptibility-weighted imaging, a specialized MRI technique sensitive to subtle brain volume changes. The scans were obtained before and after the 6-month stay on the ISS. We segmented the hippocampus into subregions using FreeSurfer subfield software. We looked at the whole hippocampus on both hemispheres: the head or anterior region of the hippocampus, the body, as well as the tail or posterior region. The hippocampal volume changes were quantified by calculating the percent change in each subregion. We also had 2 control regions. The amygdala served as a location control due to its location in the medial temporal lobe, near the hippocampus. The caudate nucleus served as a functional control due to its role in procedural memory. Our analysis revealed significant changes in the hippocampus after spaceflight, specifically the left hippocampus and its head, as well as the right body of the hippocampus. The right hippocampus in male astronauts showed greater volume loss compared to females. As well, the left hippocampal body of astronauts with previous spaceflight experience showed greater loss of volume. Neither of our control regions showed a significant change in volume, suggesting that these changes were specific to the hippocampus. Our correlation analysis with age and the change in volume also showed no significant results. The hippocampal changes observed could have been due to several spaceflight stressors: microgravity, radiation exposure, isolation, and confinement. While our study can't determine which factor contributed most, it's likely a combination of these elements. Our findings reveal a significant reduction in the volume of the left hippocampus after spaceflight, aligning with previous research which suggests it is especially vulnerable to stressors, potentially extending to those related to space travel. Similarly, we found a reduction in the right hippocampal body. This suggests that space-related stressors affect regions differently, aligning with previous research. Previous research has also suggested that sex can influence how stressors affect brain regions like the hippocampus. Our findings support this, as male astronauts exhibited greater hippocampal volume loss on the right side compared to females. These findings highlight the physical impact of spaceflight on the brain, particularly within the hippocampus, providing the first evidence of structural changes in this region as a result of spaceflight and its associated stressors in astronauts. What we learn from space missions not only helps us understand and address extreme conditions and stressors on Earth, but also shows that space travel is about reaching new frontiers, both in regards to space as well as human health.